So for this case, the critical load in the YZ direction is the lowest one, is equal to 9.462 times 10 to the power 3 Newton. Okay. So you select this one. The reason why it is having a lower critical load is how the ends are held. Right? You can see is one of the worst configuration that you can have, where one end is fixed, the other end is what? Free. Okay. So now you know the critical load, the YZ direction is 9.462. Okay. So next, we are given that the factor of safety is equal to PCR over P. Okay. So we know that from here, P is equal to PCR divided by factor of safety. And we have selected PCR. I'll write this down. Okay, so this is in the YZ direction. Okay. So when that's the case, we have 9.462. And then we are going to divide this by a factor of safety. Factor of safety given to us 2.0. Okay. So we know that 9.462 power 3 divided by 2 is equal to 4.731, okay, times 10 to the power 3 Newton. Okay. So this value that we are that are given, okay, P is equal to 4.731 times 10 to the power 3. This, in fact, okay, is our what? This, in fact, is our FAB. Okay, this, in fact, is our FAB. And we did that relationship before. This is also equal to 2.732 FAC. Okay. So this question, what did they ask for? I can't remember. Okay. Determine the maximum mass. Okay. So now we have everything now. Okay. We know that FAC is equal to 4.731 times 10 to the power 3 divided by 2.732. Okay. So 4. Is equal to 1.732 times 10 to the power 3 Newton. Okay. Therefore, the allowable mass will be equal to 1.732 times 10 to the power 3, and then the whole thing we just divide by 9.81. So 1.732 power 3. So we can take out a load of 176. 176.6 kilogram. So we'll again have to see is the structure safe or not. Okay. So usually we have to calculate the critical stress, which is critical load divided by the area. So the critical load is 9.462 times 10 to the power 3. Cross-sectional area is pi r squared, 0.025 squared. Okay. So 9.463 or 9.462 is equal to 4.819 times 10 to the power 6 Pascal. Okay. And if we were to look back at the question in the table, this is less than the stress yield, and note that the stress yield is equal to 703 times 10 to the power 6 Pascal. Okay. So I've expanded the question, okay, from the homework, because there's two possibilities where buckling will occur. Are we clear? Okay. So when there's a case, we can write out that the structure will not yield. Okay. As long as you declare this, you don't write this, I'm fine, you will get full marks. Are we clear? Okay. Right. So now I'm going to move on. We have done close to 2 weeks of buckling is under eccentric buckling. Okay. So the next topic, still under family. Okay. We are now going to look at eccentric buckling. Okay. Could you all recall what do we mean by eccentric bending? No? Okay, so let's step aside. Okay, I want you to now recall, and it's taught in 2P. Okay, so I want you to recall eccentric bending. Okay, I want you to recall that. So now if we have a structure looking like this, probably Dr. Koshi also used the same diagram. Okay. And then over here, I'm going to draw two green lines. And we have a load acting over here. Okay. And I'm going to sketch my transformation. This is X, this is Y, rotation about Z. Okay. And we have a load EY. Okay. And we can also see that we have a distance at that distance over there is E, not point E. I'm going to label this A, and I'm going to label this point B. And what we see over here at point B, we have a load, a couple load, which is your PY. And then also we have a moment. At point B. Okay, we have a moment at point B. And then when we calculate the stress, you'll be familiar with this, right? We call this stress, normal stress in the Y direction at point B will be equal to minus PY over A plus minus MZ, MZ over IZZ multiplied by a distance X. Okay. And we understand that this is due to what? And this is due to your what? Okay, that is due to your bending moment. Okay. And then from here, we know that mz is equal to py multiplied by e. You can recall that, yes or no? Right? Okay, I need a ruler. I don't say I have anger management issue. And anger management. As you all know, I run my home like I run a communist country. Don't call police on me, okay? I didn't speak. So, if you have to break something and when you pull it does not break, what do you do? Yeah. Automatically, because of our anger, we tend to do what? We tend to bend it. Yes, no. And always is a fact that the stress induced by the bending is higher than the what? External load. Are we clear? As human, unconsciously, what do? We do this. Physically, it's a good thing. Are we clear? Okay. So the bend, the moment is the one that's causing the breaking of your structure. Now this is static. Okay, this is bending. Now I want you to visualize this, how this is applied in buckling. And buckling is not so straightforward. Okay, buckling is why buckling is not straightforward. When we analyze bending, okay, over here, I want you to write this. We did not consider the elastic deformation of point B along the x-axis. Okay, we did not consider that. Okay, so now in eccentric buckling, okay, so we are going to look at eccentric buckling. So now we have a structure now. Looking like this. And then I'm going to quickly sketch the centroid. For eccentric buckling, and if this is our x, and this is our y, in eccentric buckling, the load is not applied on the centroid. And this offset is what we call what? E. Okay. So now the concern is this, okay? When we draw the free body diagram again, oh, this is getting very exciting. I'm serious. You know what? I'll see you tomorrow. Okay. I know some of you had some places to go. Now, our post homework 2 tonight. Okay.